Okay, so let's suppose a force field, F, moves a particle of mass m along a trajectory c given by r of t, where t goes from A to B, right? And then I'm going to let r of A be capital A and r of B be capital B. Right, so it moves it from point A to point B along this curve C. All right? Well, we know by Newton's second law, right? Newton's second law tells us that the force that this particle experiences, so if we restrict the force to just the path of the particle, this is mass times acceleration, right? So mr double prime. All right. Well, so how much work does this vector field F, this force field, do on the particle? So the work would be the integral along the path of F dot dr. Okay. Well, so we have a parameterization of the path. So this is integral from A to B of F of R of T, of R of T, dot product R prime of T, dt. Okay? But F of R of T is mass times R double prime. So I'll pull out the mass, and then this is R double prime of T, dot product with R prime of T. Okay? dt. But this is a very special dot product here, because this is actually A to B, d dt, r prime dot r prime. Okay? Right, so the product rule tells you the derivative of this is 2r prime dot r double prime. So if we pull out the 1/2 here, we get that. Okay. So, but a vector dot itself is just the magnitude of that vector. So this is m over 2 integral from A to B of d dt of the magnitude of r prime. But since this is a physical problem, r prime is the velocity vector. So we'll just call that v of t. Okay? So when we do this integral by the fundamental theorem of calculus, we get 1/2 1/2 mass magnitude of velocity at B squared minus 1/2 mass magnitude of velocity at A squared. But if you remember, this is just kinetic energy, mass times speed, or 1/2 mass speed squared. So this is just the kinetic energy of the particle at point B minus the kinetic energy at point A. Okay? So that's an interesting concept. But now, what if we assume, so assume now that F is a conservative force. Meaning that F is the negative gradient of some potential function, right? Now the potential function here is a potential energy function, okay? All right. So, with that knowledge, what is the work done? So the work done would be, so we're still interested in computing this, but, so let's pull out that minus sign, and since it's a conservative vector field now, it's independent of path, so I'm just going to write the integral from capital A to capital B, right? because that's all that really we need to know about is the endpoints, right? And this is gradient of P dot dr. But we know that's P of, oops, I forgot the minus sign. All right, so that's negative P of B, now I'm putting extra parentheses, minus P of A. All right, still good, still good. All right, so that's the potential energy at A minus the potential energy at B. All right, but we know from up here that that is equal to the kinetic energy at B minus the kinetic energy at A. So, what does this mean? Well, if we rewrite that in a different way, this implies that the potential energy at A, if I move this kinetic energy over here, plus the kinetic energy at A, is going to be the potential energy at B, because I move this over here, plus the kinetic energy at B. All right? In other words, the total energy of the system is conserved. In other words, this is conservation of energy. Right? So the terminology conservative vector field, this comes from here. Right? So this is how you prove that under a conservative force, you get conservation of energy. All right? So this is that stuff about, in a closed system. So there's no outside forces acting on this. All right? All right, hopefully all that made sense. Hopefully this conservation of energy here gave you a little bit of an appreciation for why the fundamental theorem of line integrals is actually useful beyond just being like a nice mathematical tool. All right, it actually has physical implications. It's meaningful. It's very useful. All right, hope you've enjoyed all that, and see you later.